Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we start into models involving exponential and logarithmic functions. It is assumed that you've watched or are very familiar with all the topics that I've covered in the videos on exponentials and logarithms thus far. For example, you should already know what an exponential function is. You should know what the natural base is. You should know about logarithmic functions and their relationship to exponential functions. You should know all the properties of logarithms, and you should be able to solve exponential and logarithmic equations and graph exponential functions and logarithmic functions. Essentially, you just need to know everything about exponential functions and logarithmic functions. The material from this point forward is really just about building exponential and logarithmic models. This would be for categories such as this one, half-life problems, and Newton's law of cooling, and Richter scale problems for logarithms, and decibel problems, that type of thing. So let's just jump into half-life problems. These are kind of my favorite of the exponential world. And so let's go ahead and dive in. I think half-life problems are awesome. By the way, the main idea with a half-life problem is somebody tells you how long it takes for a substance to decay to half of its original amount. And the equation for that is this. You get a population, and that population at any given time is based upon its initial population, but it decays to half of that population every so many years, so many days, so many hours, so many minutes, whatever it is. So if I told you the half-life of plutonium, some isotope of plutonium, was 1,000 years, then it would be P naught, whatever your initial population was, times half raised to the T over 1,000. It reduces by half per 1,000 years. That's really how all half-life problems work. So let's see how that works in this example here, example number 1. According to a study published in 2003 by the Journal of Analytic Toxicology, the half-life of caffeine, or everybody's favorite drug, ranges from 2.3 to 12 hours in humans, with longer half-lives associated with newborns, those with liver disease, and pregnant women. In this study, the scientists bought samples of Starbucks 16-ounce breakfast blend coffee each day for 6 days. Contrary to the nutritional information delivered by the company, Starbucks, the samples varied wildly in their caffeine content, from 260 milligrams of caffeine on day 3 to well over 500 milligrams of caffeine on the very first day. So it's supposed to be a specific amount of caffeine, but it varied significantly. I forget what it's supposed to contain, honestly. It could have been 240 or maybe 260 milligrams of caffeine is what it should have been labeled as. But you could see day 1, 564 milligrams of caffeine for a 16-ounce coffee, which is significantly over the daily recommended maximum allowance of caffeine, which I think is 300 milligrams. I'm not sure about that. So suppose a person purchased a 16-ounce breakfast blend containing that 564.4 milligrams of caffeine. Moreover, for the sake of this example, let's assume that this person initially had no caffeine in their system. It just makes this example much easier to talk about. And they quickly finished the coffee at 8 a.m. 5 hours after consuming the coffee, they have their blood caffeine levels tested and find they still have 351 milligrams of caffeine in their bloodstream. Find the half-life of caffeine for this specific person. Everybody's different. We all have different half-lives, that type of thing. So let's go ahead and address that question first. And I think I'll use the left-hand side of this. So let's talk about what I've handed you. I've handed you 2 values. So an ordered pair with this is time versus the amount of caffeine at that time in your bloodstream or in your system. I don't know actually how they measure it, to be very honest with you, but it's time versus a population of caffeine in your system. And we told you that initially at 8 a.m., which I'm going to let 8 a.m. be represented by t equals 0. So at 8 a.m., that person had their first cup of caffeine in a long time, 564.4 milligrams. So let's go ahead and enter that in. They had 564.4 milligrams of caffeine in their bloodstream. Just because they quickly downed that 16-ounce coffee. And then 5 hours later, as I recall from the statement, 5 hours later, so let me highlight that so you can see where I'm looking. 5 hours later, they have their blood caffeine levels tested and find that they still have 351 milligrams of caffeine in their system. I'm going to zoom in on this and say 5 hours later, we have 351 milligrams left in the system. We're going to find the half-life of caffeine for this specific person. Now remember, the formula for an exponential equation in general, I'm going to be erasing this in a moment, but in general is that. That's generally the formula for an exponential function. In this case, we're talking about half-life, so that b is going to be traded out for a half, and we are looking for how long it takes for that to decay to a half. I'm just going to actually put t here anyway. In fact, maybe I'll put t over n, mainly because I know that they're going to have, this person is going to have half of the original caffeine in their system every n hours. So I want to find out what n is. Notice how many unknowns are actually in this problem. There are 2 specific unknowns. I'll highlight them. We don't know, I mean, we do actually know what P naught is, but I'm just saying for this formula, it looks as though we don't know P naught and we don't know n. T and P of t, those are the variables in the problem. They're allowed to remain variables. But the constants P naught and n, those we need to find. So how do you do that? Well, if there are 2 unknowns, it's really helpful that we have 2 points, or 2 conditions is what we'd call that in mathematics. So let's go ahead and substitute in one of those conditions. Likely this one right here, because obviously that's a super nice condition. That is going to tell us at time 0, we have 564.4 milligrams of caffeine in the system. That is our initial amount. So this right here is P naught. Notice that I don't actually substitute it in. I want you to have a more natural understanding of the information. At time 0, this person has 564.4 milligrams of caffeine in their system. That is their initial population of caffeine in their system at time 0. I'm not going to need, I don't need to substitute that into our equation. It's just naturally, or should be, naturally understandable. So 564.4 times 1/2 raised to the t over n power. Now the next thing that we need to do is take the second point and plug that in as well. Luckily, that second point is, well, it's not super nice, but tells us that the population of caffeine in our system is going to be 351. Let me go ahead and do this. It's 351 when the time is 5 over n. Remember what we're trying to find. We're trying to find what is n in this situation. How long does it take to decay to half? All right. Well, now this is just solving an exponential equation, which is why we covered exponential equations in a previous video. Start isolating the n. Somehow we want to get that n by itself. So what we're going to do is we're going to divide both sides by 564.4. Sorry, that's kind of bulky there, but so we have 351 over 564.4 is equal to 1/2 raised to the 5 over nth power. Now you need to unlock that exponent, and that's done taking the logarithm of both sides. Remember, logarithms unlock exponents. That's a mantra. You might as well just get used to that. Logarithms unlock exponents. So I'm going to go ahead and take the logarithm, and you could take the natural logarithm if you want, or you could take the log base 10 or log base anything if you want, any positive number. But remember, you're likely going to grab a calculator for this. So you want to take the logarithm that your calculator can deal with. And your calculator likely can deal with log base 10 or the natural log. And if you're going into STEM, you might as well just get used to using the natural log. Unless you're going into engineering, then log base 10. I am going to go ahead and take the natural log of both sides, just because it's only 2 letters versus 3. No real reason there, right? So this tells us we have the natural log, I'm going to zoom out a little bit, of 351 over 564.4 is equal to the natural log of 1/2 raised to the 5 over n. Now we do know from properties of logarithms that this exponent right here can be brought out into the front of the logarithm as its coefficient. And that is the whole reason why you take the logarithm of both sides, is to unlock exponents. So we're going to go ahead and use a property of logarithms. I'm just going to say this implies. And something I should have noticed, I left the next page of this blank so that I could do all this work. But here we already have gone this far. We might as well just continue like this. To you, it likely doesn't make that much of a difference because I can always zoom in and you can see what I'm doing. So we have the natural log of 351 divided by 564.4 is equal to 5 over n times the natural log of 1/2. And I'm just going to write that as 0.5. And I've kind of highlighted that n there so that we see what our ultimate goal is to solve for n, because that's our half-life. How long does it take? How many days does it take to decay to half? Let's see. So isolating that n, I'm going to divide both sides by the natural log of 0.5. And actually, I'll go ahead and divide both sides by 5 as well. So if you do that, you get the natural log of 351 over 564.4. And again, I'm dividing both sides by 5 times the natural log of 0.5. And this should be 1 over, again, n. And we want to isolate n here. I'm not sure what that was, but we want to isolate n here. So we'll take the reciprocal of both sides. Taking the reciprocal of both sides, we get our final answer, which is 5 natural log of 0.5 over the natural log of 351 divided by 564.4. And that is equal to n over 1, but just n. That's the number of hours, because that's the units we're dealing with here, right? Just double check. Yeah. So notice where I had highlighted here 5 hours. Once they give me a time unit, that's the unit for the problem. So hours is the unit for the problem. So this n is the number of hours that it takes for the caffeine in this person's system to reduce to half of its original amount. Remember that n is from this original formula. The population of caffeine in their system is just the initial population, and it reduces by 1/2 every n hours. And so we just solved for n to find out, well, how long is that? How many hours? And that requires a calculator. So I'll just quickly grab a calculator. And just to showcase, a lot of people go to Desmos and think it only has a graphing calculator. It actually does have a lot of other calculators there. So I'm going to go and use the scientific calculator here. And you see this beautiful calculator come up. And we had 5 times the natural log of 0.5 being divided by the natural log of, and then in that natural log, it was 351 divided by 564.4. And you can see off to the right there, it's 7.3 hours. And so back here, I could just say, great. The half-life for that person is, for the caffeine in that person's bloodstream, is roughly 7.3 hours. I just rounded it to a single decimal place because I wanted to. I will probably use this exact version of n for any future computations. And I'll show you how to do that in Desmos. You have a answer button or a save button in your calculator where you can save these values, but I'll show you in Desmos how to do it. All right, so to answer question A, find the half-life of caffeine for this person. It's roughly 7.3 hours. And now they're asking, how long will it be before the amount of caffeine in this person's system decays by 10%? I'm trying to really get you to think about words here. If you want the amount of caffeine in this person's system to decay by 10%, that means that they still have 90%. It's only decayed by 10%, so they still have 90% in their system. So for this one, I'm actually going to go to the next page so that we have a clean page to work with. And I'll just zoom in there. Now remember, we have a full actual formula now for the amount of caffeine in this person's system at any given moment. So the formula is going to be P of t is equal to the initial amount, 564.4, times 1/2 raised to the t over n, where n is that value that we found just a few moments ago. It's 5 natural log of 0.5 all over the natural log of 351 over 564.4. So that is the value of n that we're dealing with. So we have all our constants have been found. And we want to know, how long does it take for only 10% to disappear? In other words, they still have 90% of that 564.4 milligrams of caffeine in their system. And this is such a special problem that it's important for you to really pay attention. Well, you should pay attention to all these problems, but this part is critically important so that you really understand that this initial population doesn't matter. So let's say that I want 90% of that to remain. 10% of it has decayed, so we have 90% left. Well, that means I want my population to be 90% of 564.4. So we had this initial, so all I'm doing is substituting in to this right here, the population function. I'm substituting in, I'm pointing in the wrong spot. I'm substituting in right there. Our output should be 90% of 564. So I'm going to solve this equation for t. I want to know, remember, n we know. I want to know what t is because it's the only thing we don't know in this problem. At what time do they have 90% still left in their system? So let's go ahead and start isolating that t. You'll divide both sides by 564.4, and when you do that, so divide by 564.4, when you do that, you'll see that on the left-hand side, the 564.4s will cancel. And that's the critical part I want you to pay attention to, is that it turns out this question, how long does it decay, how long does it take for the caffeine to decay by 10%? Well, that doesn't really matter. Our population doesn't matter, our initial population of how much caffeine we have in the system. The amount of time it takes for 10% to decay is the same if we had 1,000 milligrams of caffeine in our system or 1. It's all the same amount of time to decay by 10%. Now, solving for t, we'll take the natural log of both sides. Again, you're welcome to take the log of both sides, log base 10, but I just don't like to do that. I like the natural log for some reason. And notice when I do this, I actually immediately pull the exponent off. You're at this point now in your mathematical career that you know when you take the natural log of 1/2 raised to a power, you can bring that power outside. And then I will divide both sides by natural log of 0.5 and multiply both sides by n. So multiply by n and divide by the natural log of 0.5. It's just me justifying my moves. So I'll have n natural log of 0.9 divided by the natural log of 0.5, and that should be the amount of time it takes for 10% of the caffeine in this person's system to decay, or in other words, that they still have 90% of that caffeine in their body. So I told you I would show you how to use Desmos to save that value of n because we need to use it. So let's go over to Desmos very quickly. Here we are in Desmos. You can just hop over here and just call this n. You can say n equals that. And now I can use that in future computations. The computation that we're dealing with is n times the natural log of 0.9 divided by the natural log of 0.5. So roughly 1.1 hours. I'll hop back over and just say that that t is approximately 1.1 hours. So that's how long it will take for 10% of the caffeine in this person's system to decay, considering that their half-life for caffeine in their system was 7.3 hours. And there I just filled that in. So again, pay close attention to that wording. How long before the amount of caffeine in this person's system decays by 10%? The second question, part C, how long before the amount of caffeine in this person's system decays to 10%? So at that is a different question. I want this caffeine to decay to 10% of what it originally was, which means I've lost 90% of the caffeine. And this is what most people think of when they hear the problem. They want 10% of the original amount. So let's go ahead and hop over to that blank page there. Excuse me. And we know we're still dealing with the same function right here with the same n. And we know we want the output population to be 10% of the original population. And when I say population, I mean the amount of caffeine in the system. And I hope you understand from the part B example that the initial population actually doesn't matter. We really want to solve this equation. When do we have 10% on the left-hand side? That's really what we want to solve. The 564.4, again right here, just didn't matter. We end up solving 0.9 equals in that case because we wanted 90% left. But in this case, we want to know when do we only have 10% left. The mechanics are identical. And in fact, you can almost just copy this formula right there. Just replace the 0.9 with a 0.1. And natural log of 0.1 over the natural log of 0.5 is equal to t. And remember, we know what n is. So again, I get to just hop over to Desmos here. Now notice how much faster that was to set up. It was because we already pre-did a different problem, so we knew the form of the solution here. The only difference between the previous form and this is that the previous form had a 0.9 because we wanted to know when we had 90% left. And this form has a 0.1 because we want to know when we have 10% left. So I can just go over here and I actually technically, I think, can copy. Let me Control C that, hit enter, Control V, and I'm just going to go ahead and replace this with 0.1. And you can see to get 10% of that original caffeine left in this person's system, they'll have to wait 24 hours. That's how long it'll take for their system to flush out all that caffeine. And by the way, 564 milligrams of caffeine is an insane amount of caffeine. And like a cup of coffee is about 50, maybe 60 milligrams of caffeine. So this person still has a standard cup of coffee in their system 24 hours later. So as we just saw there, the amount of time that needs to pass is roughly 24.2 hours before this person would have only 10% of caffeine remaining in their system. And there I just filled it in on that part. And then finally, part D. Suppose this person suffers from insomnia if they go to bed with more than 80 milligrams of caffeine in their system. Well, with that drink at 8 a.m., when can this person possibly go to sleep? Well, let's find out. They had it at 8 a.m. Let's say it was 8 a.m. on a Monday morning they had that drink. When can they go to sleep if they will suffer from insomnia if they have more than 80 milligrams of caffeine in their system? Well, I'm going to write it down below. We want the amount of caffeine in this person's system to be less than or possibly equal to 80 because, again, they can't go to sleep if they have more than 80 milligrams of caffeine in their system. So we just want the amount of caffeine in their system to be less than or equal to 80 milligrams. And remember, our population formula was this: 564.4 times 1/2 raised to the t over n, where we know what n is, and we want that to be less than or equal to 80. In this case, the initial population is very important because we're not talking percentages. I don't want to know when they have 80% left. I want to know when they have 80 milligrams left. And knowing how much they started with is critical. So that is important here. We'll divide both sides by 564.4, right? And when you do that, you get half to the t over n power is less than or equal to 80 over 564.4. Notice all these problems kind of come down to the same thing. You're just taking natural logarithms of both sides because you're trying to find out what the time is, how long before this person can go to sleep. Take the natural log of both sides. Again, you could take log base 10 if you want. And we get t over n, natural log of 0.5 will be less than or equal to natural log of 80 over 564. Whoops, that's supposed to be a 64.4. Now here's where things get a little tricky because a lot of people, if they're working with inequalities and logarithms, forget something about logarithms. This number right here is a negative number. Natural log of anything less than 1 is negative. And so if I divide both sides by the natural log of 0.5, the inequality is going to swap. Let me just do that single step. We didn't have to worry about that before because we were never working with an inequality. But at this point, yeah, we know that natural log is negative. Natural log of 0.5 is negative. And so when you divide both sides by that, the inequality has to flip. And then we're going to multiply both sides by n. And you might be wondering, is n negative then? Well, let's take a look at what n is. It's 7.3. That's not a negative number. So when I multiply both sides by n, I don't have to flip the inequality. This is just going to imply that t will have to be greater than, this person can go to sleep at any time greater than or equal to n times whatever this number is, right? So that's how many hours it will take before this person can go to sleep. And I don't know about you, but, well, I'm older than probably anybody who's watching this video, but I will just say this, that as you get older, a teeny little bit of caffeine in your system can keep you up for quite some time, and it's very annoying, even though we all love caffeine. So let's go ahead and go to Desmos and figure out what this time value is. There's all our previous work right there. Let's see, we want n times the natural log of 80 divided by 564.4. Hop outside that natural logarithm and then divide that by the natural log of 0.5. And you could see it's 20.6 hours. All right, so I'll write that down. This implies that t will have to be greater than or possibly equal to 20.6 hours. By the way, that's a rough approximation, but good enough for me. So let's see, 8 a.m. is when this person had this coffee. That'd be about 4:30 in the morning. 20 hours later, basically. 20 hours after 8 a.m. is 4 a.m. and another roughly half an hour. And it's going to be about 4:30 in the morning that this person can actually go to sleep. Roughly around 4:30 in the morning. That sucks, especially if this person works every day at 8 a.m. That's just terrible. So this is a great problem. I do this style of problem every semester whenever I have a course that involves exponentials, which is pretty much every course that I teach. But when I'm teaching exponentials, I love this problem because it really does showcase how Half-Life works in the world around you and in your daily life. And if you don't think Half-Life affects you, and I'm sure you're not like that, I'm sure you would agree that Half-Life affects you somehow, then let me just tell you this. If you're on any type of medication for whatever condition you might have, you're likely taking a medication every day or a couple times a day, or if you're on the pill for contraception or something like that, you take that daily. There's a half-life associated with those, and that's why you have to take those pills daily, because that amount of dosage in your system spikes when you first take it and decays to below what we would consider to be a safe level. And so then you take your next dosage and it spikes back up. The next dosage usually spikes a little bit higher, and it takes longer to decay to the below the threshold. But that's why, for example, contraceptives like the pill, they get weaker in dosage as time goes on, is so that you don't have the spike going up and up. Instead, the dosage gets less and less, so you have this maintenance dose every single time. Anyhow, very, very interesting stuff, very applicable to real life. So that's it for this video. I will see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.